Example number 3, and I'd rather do it the whole thing again, even though we already had sort of halfway through. I'd rather do the whole thing again. Okay, so a colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the time in hours, express n as a function of t. And well, all we do is express n as a function of t, and that's the n initial, that is the initial population or the initial amount of bacteria in our Petri box, so to speak. Usually that's what we do to grow bacteria, right, in the biology lab. E to the kt, where k it measures how fast the growth goes. You know, again, in analogy with finding the slope of a straight line, that straight line gives us the rise over run or the dive over run, you know, depending on the situation, whether we have a positive or a negative slope. In a similar way, we have this sort of slope, which is not necessarily a slope. It's actually the growth constant or decay constant, depending on the sign. And t is whatever time. Of course, this is a baby model, because ultimately, I mean, think about the domain of these exponential functions. Well, it's all real numbers. That means t can be anything, all the way to infinity. But really, if t becomes infinity, the population also becomes infinity in this case. Well, but for example, in our planet, do we have room to allocate infinitely many people, for example? Infinitely many bacteria? Maybe large numbers, of course, but that's not that's not like infinitely many. And in fact, bacteria will die at a point, like people dies at a point, you know. So there's no way we can just live forever and populate the planet forever. So there's actually a better model, a better growth model for these kinds of situations, which is the logistic growth model. And well, the logistic model actually considers the carrying capacity of the room, the city, the planet, well, depending on the scale where it's happening. Like here, well, the carrying capacity for this classroom is the number of people it can allocate. I think it's 101 students or something like that. All right. So in reality, that's what happens, and also because supplies run out, you know, such as food and services, etc. Well, so this model is really unrealistic, if you will, right? But still, it's a good model to practice our exponentials and logarithmic solvings and all that, of course. Those of you who are going to take biology, you will see a lot more about this. Or math majors also look about this. Well, if the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture. So number one, let's highlight this same sentence right here. The number of bacteria doubles in 3 hours. But notice, check this out. Notice they're not telling us how much bacteria is at the beginning when we start making the measurements here, right? So they're not telling us anything, and you will find out how it really doesn't matter. So you'll see. Well, so from here in words we can make the following. So from here, this means that when t equals to 3, and notice t is in hours and n is in grams, n initial, n sub 0 if you will, becomes 2 times n initial. Well, that's basically how we interpret this sentence in words. Now we need function notation to describe that sentence in words. That means that from here, that means n of 3 equals to 2 times n sub 0. That is, when we plug in our function at t equals to 2, that population size will become twice as much as we had initially. All right, now what's next? Well, let's use this to find the constant, the rate, the constant rate, the growth constant actually, because well, we're gonna have sometimes different what else? Different amounts but we need to know the rate of growth in this case. So, well, so starting again with n of t equals n initial e to the kt, to the kt, we can go about, well, n of 3 equals n initial e to the k times the quantity 3. Well, on the left-hand side, they're telling us that when n equals to 3, when n is evaluated at 3, we get twice the amount of the population and e to the 3k. And well, notice how the NOs, the N initial goes away on both sides of the equation. So in the end, we really don't even care about what the population size will be. So it's independent of the initial population. That's what we're trying to say. So that's 2 equals to e to the 3k. And well, I'm leaving a space here. I think you're seeing why am I leaving this space right here, because well, our target variable here is the letter k, the growth constant. So, but that's part of an exponential function. So we need to get rid of the exponential by doing the inverse operation on both sides of the equation, which in this case is ln. And ln cancels out with the exponential, and we get 3k equals to ln of 2. And solving this baby equation for k is ln of 2, ln of 2 over 3, which is approximately 0.23, 2311, rounding to 4 decimal places. All right. However, in practice, you might want to keep all decimals when coming up with calculations actually. And again, careful when evaluating these logarithms, because actually these are really easy to make silly mistakes. So for example, so what was that again? Okay, I'm gonna make a mistake on purpose here, ln of 2 over 3. And notice we even got a negative value here, right? And well, if that's the value of k, and if that's negative, then this result so far contradicts the situation we're working on, which in this case is that of an exponential growth, not a decay. That means we made a mistake over here. So, and in fact, it's the division by 3, what went wrong. So when you type the ln operator on your graphing calculator, it's going to open parentheses by default. Type the argument. Once you're done typing the argument, make sure to close parentheses. When you close parentheses, you may go about the division. And that's our result. All right? So, actually, I got the wrong rounding. So, 1, 0. All right. That being said, so let's see, find a function. Okay, so they're asking us to come up with a function, so we may go about the function and replace k with the value we just obtained in all this process. So n of t equals n initial e to the 0.2310 k. All right? And again, because somewhere in the calculation that n initial got canceled again, this process is not dependent of the initial population. It's all about time versus amount. That's all it is. At least for this simple situation. So that's our model. And you can go about your favorite n initial, 5,000, 5 million, 93 zillion, whatever amount of, oh, wait a minute, no, this is measured in grams and not in number of bacteria. So 5 grams, 7 grams, or 0.1 gram, whatever. Now the question is, How long will it take for the size of the colony to triple? All right, so that is. How can we? Okay, so let's interpret this in kind of words first. So for n initial to become 3 times n initial, the question is, what's the time required for this? All right. So we don't know. That's the question. So we're going to go about the previous model here. Let's go about the previous model, and let me write it down. N of t equals n initial e to the 0.2310 t. And we want to know what's the value of t for which we will get 3 times n initial. And again, see how n initial cancels out. And well, dividing both sides by n initial. This is how, again, we keep verifying that the initial amount doesn't really matter. So cancel, cancel, and let's see. So that's e to the 0.2310 t, and equals to just 3. But I'm leaving a space, you know what's that for. And that's to take the ln. So let's take ln to both sides. And that's going to get this canceled. And 0.2310 t equals ln of 3. Divide both sides by the coefficient of t, and that's going to give us the time required for the initial amount to triple. So divide by 0.2310, 0.2310, cancel, and t equals to, I have approximately 4.755 hours. So almost 5 hours, pretty much, to have the triple of the population that we started with. All right. And again, we really didn't even care about the initial population, right? Well, so these first couple of examples on applications were about exponential growth. The next example that we're going to look on the next page is about decay. Well, it's going to be pretty much the same, and decay is mostly used by archaeologists. It's also used in forensics, for example. Based on a sample they take from a dead body, they can calculate how long that person it's been dead for, right? So, well, and they can come up with the exact amount of time because it's based on this same chemical procedure they do in the laboratory based on an exponential decay. And well, it's similar to the situation we're going to look at. So, and what do we have? Traces of burned wood along with ancient stone tools in an archaeological site were found to contain approximately 1.67% of the original amount of carbon-14, which is one of those radioactive isotopes of the carbon atom. And if half-life of carbon-14 is 5,600 years, all right, that's something we might want to highlight here. The half-life is that amount of time. Approximately when was the tree cut and burned? All right, let's see how long had those ashes been there at the archaeological site. And again, in this case, for decay, it's a very similar model, except that we're going to have a negative k, and that's to denote the decay. All right. So we're going to start with that. N of t equals, let me write it again, Uh, anyway, hmm, what's this? What is that? Uh, Half-life think about? Well, let's see. That means it takes 5,600 years to have our initial amount to be half of what we had. For example, n evaluated at 56,000 equals to 1/2 n initial. That's what it means. That's the function notation that we write from that sentence that we're going to later implement over here. All right. So let's see. So n of t, if we evaluate, for example, n at 5,600, that equals n initial e to the negative k times 5,600. All right. But now we are going to replace this function notation with its corresponding result, which is 1/2 of the initial amount. So what, and again, whatever that initial amount, we don't care. We really don't care, because it's all about amount after any particular time versus time, and not, and the initial amount doesn't vary. It's that initial amount, and again, it's just the initial. So that's a 1/2 n initial equals n initial e to the negative k. Let me write 5,600 k. And then from here, let's solve the equation for k rather, because we need a decay growth. I mean a decay constant rather. So let's divide by n initial, cancel n initials, cancel n initials, and what are we going to get? ln, oh no, not ln yet, 1/2 equals e to the negative 5,600k. All right, so well, again, I left this space on purpose because you know what's next, right? Because we want to find k, and it's part of an exponent of the exponential function. We need to get rid of that exponential by doing the inverse of an exponential function, which is ln. And it's not just any logarithm. I mean, you could do whatever logarithm you prefer, but I mean, in this case, since we have the natural exponential, that is the exponential base e, come on, we can do just ln of e like this. All right, that's going to leave us with negative 56k equals ln of 1/2. And finally, k equals ln of 1/2 divided by negative 5,600, right? Which approximately, computing this, approximately going to give us 0.000124. Okay. Well, that's the result I obtained using the graphing calculator. Let me show you how do we do this in the graphing calculator. And again, I take the time to do this just so you guys don't fall in those potential pitfalls, syntax errors on the graphing calculator. So let's see. ln 1/2, but well, that's only the argument of the natural log in the numerator, close parentheses, and we may go about the division by negative 5,600. But I still got a syntax error here, and that's because I used the wrong negative symbol. I used the symbol. This one right here is the symbol to subtract. That's the one below the multiplication and above the addition. In this case, we should use the symbol to change the sign to get the negative of a number, and that's the one next to the enter and between the enter and the decimal place. Only then, that's our result. Well, I got the result as in scientific notation, but when I did it on my notes, so what's that? 1.24 times 10 to the negative 4. That's the same as saying 1, 2, 3, 4 places, and fill in the remaining spaces with zeros. So that's 1, 2, 3, 0.123 zeros, 124, which is the same result that we obtained here. And the reason why I mentioned this is because, well, when I'm going over these exercises, sometimes I just give you the results in decimals. But again, I'm also taking some time to discuss how do we go from scientific notation and the decimal form, because when using these results to put them in the formulas, you want to go back to the calculator and you don't want to type scientific notation numbers. So you just want to use decimals for more practical purposes. Okay, and for this kind of decay problems dealing with radioactive decay and what else, and archaeology, geology type of problems, usually you will get these really tiny results, and that most calculators output in scientific notation. Although I believe you can set up your calculator so it doesn't give you scientific notation and it gives you decimal. I don't know how to do that, but I just go with the rules to change between one notation and the other. All right, so that's our decay constant. Now we may go about writing the corresponding model, or the model with its corresponding decay constant. And well, and we can go about answering the other questions. So they're also asking us, or they're rather telling us that that the moment where the sample was taken and taken to the lab, rather, when it was taken to the lab, they did the chemical process and they found 1.67% of carbon 14. All right? So what does that mean? That means, okay, let me write down a sentence first. With 1.67 of carbon 14 present, that means that N initial became 0.0167 of the initial amount. All right, that's what it means. And that happened after an unknown and well, that unknown time is actually the question, right? How long ago? When was the tree actually caught and burned? All right, so let's find out. So that means we're going to replace N of t, so N initial e to the negative 0.000124. We will replace this amount right here over here, and then solve the equation for t. And by the way, I forgot to write that initial symbol. That's N initial, by the way. All right, so that's a 0.1, oh no, 0.0167, and initial equals N initial e to the negative 0.000124. All right. Let's divide both sides by N initial, and notice again how N initial cancel. And again, we really don't know. The advantage of these exponential models to determine the age of a tree, which is essentially what we're doing. Uh, they're very convenient because again, notice the amount, the original amount of ashes or traces of the tree. We don't need to know how much it was. We don't need to know if that tree was maybe 3 feet tall or 27 feet tall. We don't care about it. All we care it's the chemical part in this, because the amount of traces after that amount of time. So, which is great. Otherwise, well, that's how archaeologists date like pieces they find in like, for example, in Egypt or in many archaeological pieces. So they take a sample of that ceramical piece or metal piece and do the chemistry on it, check the amount of carbon, and basically this exponential model. And well, let's see, 0.0167 equals e to the negative 0.000124. And again, I left this, the space right here for ln, and first of all, cancel the ln with e right here, and what's next? Negative 0.000124 equals ln of 0.0167. Divide both. Oh, that's a t here. Forgot a t. Yep. Little typo, I forgot a t here as well. And divide both sides by negative 0.000124. And t equals whatever number this is. And it's going to be a really big number because we're dividing by a really tiny number, divide by a really small number to get a really, really big number. Which is approximately 33,003 years. All right. Because I mean, if it's 33,000 years ago, there's no way we can know how big the tree was, really, right? So, really don't know. All right. Let's look at the next at the next topic. Next, and I believe this is the last topic for the section, and I think it's also the last section in the chapter. And then next time, well, I don't know if we're gonna get the chance to finish the whole thing today. Maybe we get halfway through the problem. This one is gonna take a good minute to go. All right. So let's see, Newton's law of cooling. What's Newton's law of cooling? Well, there's a bunch of ways to put this in context. Well, essentially, you have a really, really hot piece, whatever, a metal piece, or like for example in metallurgy, for example, when they melting metal at say 600 degrees, and we're making these alloys like nickel and I don't know, iron, they will later be used for constructions or for cars or airplanes parts, depending on the purpose. Well, initially they're taking out of the mixer, where they do the chemistry to come up with these alloys, and they just let them cool for long periods until they sort of reach or they even out with the room temperature. So that's pretty much what Newton's law of cooling is. Or another example, like a pizza, for example. We usually, the other day went to Domino's and I looked at, it was the oven, I believe it was 460 degrees. So the picture here is, well, you get the pizza out of the 460 degree oven, and well, with time, the pizza just cools down, right, to room temperature. So that's what this model is about. What do we need to know in this case? Well, the temperature at which the object initially came out either of the oven or the metallurgic mixture, whatever it is, and the temperature of the surrounding, the temperature of the room in this case, right? And well, and what else? Well, of course, those are constants, and then in this case, we are still going to go back and forth um, between any temperature at whatever time and times of time, of course. And well, notice in this case, we need to be very careful. Although the formula does not depict this this idea, I mean, k is negative, so when we find that constant, it's going to be a negative value because, I mean, if we think about law of cooling, well, cooling sounds more like a decay in the temperature, right? So let's see how far can we go about this problem. So an object is heated to 100 Celsius, to 100 degrees Celsius, and then is allowed to cool in a room whose air temperature is 30 degrees Celsius. All right. So that's our U initial, if we will. The temperature at which is with the highest temperature, so that is U initial. And what else? T, I guess this is T. Yes, this is T. Let me use a different highlighter here. Room temperature. Room whose temperature is T. All right, that's the temperature of the medium, if we will, the temperature at which that hot object will even out its temperature. All right, so let's see, if the temperature of the object is 80 Celsius after 5 minutes, when will its temperature be 50 degrees? Oh my God. Well, that question, despite it looks like, I mean, like very short question and looks like very simple, well, there's a lot for us to figure it out. Now, because we need to figure out the value of K, and then we will have to find the value of T at which the object will be, what's that, 50 degrees Celsius. So let's get started with it. So number one, okay, let me restate the model. U sub T, which is equal to the temperature of the medium at which the object is cooling, and then plus U initial minus T, e to the KT. All right? Well, so, and of course it makes sense to have to subtract the room temperature from the temperature at which the object is being heated initially, because I mean, uh, large number minus smaller number, that has to be a positive result, because otherwise if we get the reverse, we're going to get a negative temperature. And if we think about it, I mean, for example, the pizza example, for which it's coming out of 460 degrees, and the room where the pizza is 30 degrees. Well, if you do the reverse, you're going to get something like negative 90 degrees Celsius. And come on, it doesn't make sense it doesn't make sense to be too low below zero. You will be dead most likely at that temperature, right? Frozen. Okay, so that's how we can verify or check those results for consistency. So that's why we subtract the smaller from the larger. All right, so let's plug in numbers. That is U of T equals the temperature of the room, which is 30 degrees Celsius, and don't need to write down any units for this, plus U sub 0, which is 100 degrees minus the room temperature, e to the kt. And we can simplify this. U of t equals 30 plus, what's that, 70 e to the kt. All right? Okay. So we have a simplified model, but this model is lacking its decay constant. That is how fast how fast this object is cooling. Well, we have information for that. We can use this information here. Let me highlight it. So the temperature of the object is 80 degrees after 5 minutes. We can use this piece of information here to find out the value of K. That means from here we say that U of 5 equals 80 in function notation, that the temperature is 80 degrees after 5 minutes when the object was taken out of whatever oven or chemical mixture, you name it. We don't know what the object is anyway. Well, so from here, if we do the following, U of 5, that's a 30 plus 70, e to the k times, what's this, 5. Well, we know U of 5 equals to 80. That's 30 plus 70 e to the 5k. And we have one of those baby exponential equations for us to solve. And I call it baby equation because it's one of those that contain only one exponential term, not like the weird ones we did at the end of the section that contain two exponential terms. You know, we had to come up with some sort of a quadratic pattern or the like. So we can easily solve for k here. That's going to be 70 e to the 5k, and subtract 30 from both sides to get 50, and then divide both sides by 70 to get e to the 5k. Come on. E to the 5k equals, divide both sides. Okay, let me do this division. Let me do the subtraction also. Minus 30, divide by 70, divide by 70. Well, we can divide out the zeros, and that's 5. Oh, let me leave some room. You know what for? You know what do we do for? 5k equals to 5 over 7. And again, that's to take ln on both sides. So cancel ln with e to leave us with 5k equals ln of 5 over 7. And finally divide both sides by 5 to get k equals to ln of 5 over 7 divided by 5. And be careful when expressing these results, these exact results by hand, because make sure for syntaxis to put parentheses around the argument of the natural log, because it could be the case that you may feel like compelled to multiply or simplify this complex fraction, which is not. All right, this belongs to the natural log, and this denominator is its own factor. And in this case, we can use our graphing calculator to simplify this result, and I got this to be negative. I'm going to put it here, negative 0.0673. And how about we do that in the calculator again, just so I can show you how do we get this result. So ln of, what's that, 5 over 7, close parentheses, very important to close parentheses, and divide by, what was that, by 5? Yes, by 5. Divide by 5. And that's pretty much our result, isn't it? All right, now that we found that value for k, notice it's a negative result. That's because we're talking about a decay in the temperature. All right, so let's just write down our model. Where do we go for the model? From here, write it down over here and turn this into u of t equals 30 plus 70 e to the negative 0.0, oh, this is 0.0673 t. All right, and you know what, I think we can stop here.